serious concepts that are going to have important uses for the rest of the class. And one of the concepts that I've introduced is the concept of work done W. Now I've told you that W is the dot product. This is a dot product, it's not a normal multiplication, of two vectors, the force F and displacement x. And the picture that you should have in your head is you have a certain mass and you're applying some force that gives it a certain displacement. So if you think about it, it's a pretty high level description. We are not getting into acceleration, we are not getting into velocity, we are not getting into many things. We are just saying there is a force and the force results in a displacement. High level in the sense that we are removing many details of the problem already. Now that is usually associated with building a tool that is more powerful than the more detailed tool that you have used so far, which would be kinematics. So in this case it is very simple because the displacement is from left to right, the force is from left to right, the force and the displacement are parallel, and therefore according to the dot product formula, as I showed you on Tuesday, what you are doing is really taking the magnitude of the force, the magnitude of the displacement, and the cosine of the angle between the force and the displacement. If you have two parallel lines, what is the angle between the two lines? 0. So that means if these two are parallel, you have cosine of 0, but cosine of 0 is 1, right? So from the definition of a dot product, essentially this is F times x, where by F I mean the magnitude of the vector force F, and by x I mean the magnitude of the displacement x, it being implied that both are in the same direction. Now suppose I do the very same thing, excepting that I've already pushed this block, I've given it a kick, and I notice that although I've given it a kick, it'll stop after some time. Let's say it gets displaced by some distance x again, but then it stops here. And I've kicked it here. Okay? So we can study a problem like this. So I've given it a kick, and basically what happens is that it started moving initially, and then the friction force essentially kills the motion. So as it moves, the friction force is the only force that's working on it. That will be opposite to the direction of motion, which is left to right. So we already know how to describe friction force, F friction. F friction in this case, because there is motion, there will be a kinetic coefficient of friction. This is a flat surface, which means if the mass is m, you have mg downward. So therefore, this would be mu mg. So you see the work done by the friction force, let's call it W friction, the work done by the friction force, not by the kick itself, is going to be that friction force, F friction, times x. But you have to be careful. The friction force is opposite to the direction of displacement. So if two lines are opposite to each other, otherwise parallel, anti-parallel that means, the angle between them is 180 degrees. So friction force is going to be that way, displacement is going to be that way. This angle therefore will be 180 degrees. So therefore you have to put in a cosine of 180 degrees, which means you have minus F friction times x. Okay? So what it means is that the friction takes energy away from the system. That's what it's doing. It's taking energy away from the system. And because of that reason, although you gave it a velocity v, it will eventually stop after moving x. Okay, that's basically what it means. The other point that I discussed last time is that you have the work energy theorem, and the idea of the work energy theorem was work done is somehow, or delta of work done, little bit of work done, small amount of F dot delta x is essentially final kinetic energy minus initial kinetic energy. Okay, so actually one of the points I was making last time is that this is a very powerful statement. Why? This is something that we called the work energy theorem. The reason why it's a very powerful statement is because for the first time you are actually dealing with work done by a dissipative force. Dissipative forces are different than regular forces like gravitational force or force due to a spring. In dissipative forces, energy is not conserved. Energy is being taken out because it is a dissipative process. So here you actually are seeing that you're actually using an energy related equation where what you are using is a dissipative force. So I want you to be conscious of that. That is necessarily different than a natural normal force like gravitational force and so on. So here we have used a dissipative force. So just make a note of the fact that this is work done by a dissipative force. Okay, that's what this is. It's not always the case, but in this case we have calculated work done by a dissipative force. Now let's go back to more well-behaved forces. I want to show you something in a little bit more detail. So suppose here is a mass I have at point A, and this is point B. Okay. This is what I would call the ground level for now. In all these problems, you will see that the ground level is very important. Why? Because in the ground level, you are actually setting, just like before, your y equal to 0 level. Okay? Your 0 vertical height point. Why is that important? Because we are going to be dealing with what we will call potential energy. And potential energy is the energy by virtue of where you are, by virtue of your configuration, by virtue of your position, by virtue of your placement. That's what potential energy means. So in other words, when you say y is equal to 0, that means you are setting the 0 of potential energy. That's what it means. So in this case, if I have a mass here sitting at height h, I know that there is a downward force mg if m is the mass. So if this mass travels from A to B, let's say falls from A to B, then what we have is we have a work done W, which is going to be mg times h. mg is downward, h is downward, they are both parallel, cosine of 0 is 1, and that is what you get. W is mgh. Okay, so if W is mgh, then by work energy theorem, which is what we worked here, this should tell us that 1/2 mass times velocity at B square, which is the kinetic energy at B, minus 1/2 mass times velocity at A square must be equal to mgh, right? That's what we learned. So this is something that I did on Tuesday. But if you pay a little bit more attention to it, you can also see that I can rewrite this as h being, left-hand side being mg ya minus yb equals 1/2 mvb square minus 1/2 VA square. Okay? Why did I do that? Well, I did that with a specific purpose, and the purpose I want to show you that in this case, just by using work energy theorem, because we are not using a dissipative force, I can rewrite this equation as mgya, which is potential energy at ya plus 1/2 m va square. Since that has a velocity square, that is what we will call kinetic energy. Energy by virtue of motion is mgyb plus 1/2 mvb square. This is something I had on the board last time also, but it was towards the end of the class and I was not able to do as much work on it as I would have liked to. So what I'm trying to do is I'm trying to illustrate to you how powerful work energy theorem is as a tool. Which is the reason why I'm emphasizing this so much. So work energy theorem basically allows you to calculate work done. What happens to this work done? Well, this work done can be energy lost by a system depending upon the force and displacement. This work done can be energy gained by a system. This work done can be because of something like friction, which is a dissipative force. This work done can be because of gravity, which is a natural universal force. So it's a very powerful tool in which I'm using all kinds of forces to get my work done. But this powerful tool delivers something which is pretty interesting now. This is a statement of a fundamental law of nature, which is energy conservation. Energy conservation basically tells us, fundamentally, that energy cannot be created or destroyed. That is technically the statement of it. You can't just invent energy out of nowhere. The universe had a certain amount of energy when it began, and that energy remains in the current universe. So for the last 13.5 billion years that the universe has evolved, the amount of energy contained in the universe, according to this law, is the same. So we are not going that deep, but in this case we are saying that the total energy that the system had at A, so let's call it EA, and the total energy the system had at B, EB, they must be the same because energy is conserved. So in other words, this is the total energy EA and this is the total energy EB. So for us, we are not dealing with things that are charged and this and that. We are not doing that. We are simply dealing with mechanical systems. That's what 101 is. We are dealing with mechanics, so mechanical systems, as opposed to electrical systems and so on. So in mechanical systems, there are two pieces to energy that almost always enters. There is a third piece that we'll add after midterm 2. So this part of it has a y in it, and y has to do with location or position. So this is therefore energy by virtue of position or location, and that would be potential energy. Okay? And this part is by virtue of motion, and that will be kinetic energy, KE. Similarly here, it's potential energy and kinetic energy. So in other words, you're saying that the kinetic plus potential energy before, which was at A, is exactly equal to kinetic plus potential energy after. That's what you're saying. Because total energy is neither created nor destroyed. So this is not a great surprise, but it's actually technically, if you are trying to do an experiment to see if it's true, you'll run into all kinds of trouble. Because if I drop something, I don't want to drop something actually, because it'll probably break. Well, I can break this. So this is mgya. I'm holding it at rest. So therefore, VA is 0, right? So its total energy is going to be whatever this height is times mg. That's the left-hand side, EA. This is a EA. Now if I drop it, what we are assuming is that just at the point it falls, energy is conserved. Well, energy is actually conserved almost, except for air getting in the way, just before it falls. The moment it falls, things get complicated because there is sound, there is some inelastic motion by which it jumps up, so we are avoiding that point. So when we are using energy conservation law, bear in mind that we are ignoring the effects of air. We are actually assuming this is in vacuum. Why are we doing that? Because physics allows us to do that. In vacuum, the dissipation is very low, zero. In air, the dissipation is very low actually, unless the column of air through which it passes is very large. So let me just take this argument a little bit further. Let us say that in going from A to B, instead of taking the direct route, you actually want to slide down an incline. Want to slide down an incline. And let's say this angle here is theta. And let's say this height here is h, and the length of the incline, which is the hypotenuse of the Pythagoras of the right triangle, is L. So now we know what's going to happen. This mass is going to go down this incline. Let's say it slides down the incline. So what will happen is that along the incline, it will have mg sine theta as the force along the incline. This is the mass here, sliding down. That's something you already know, so that's not a big surprise. Now, it travels a distance L. Now, sine theta, by definition, is the height divided by the hypotenuse. So sine theta is h over L, which means L, the distance traveled, is h over sine theta. So let's call this point C. So what we are saying is that this is the force. Force times L is h over sine theta. Okay. So this piece here is nothing but L. This is the force, and that must be equal to 1/2 mvc squared, because that's the kinetic energy at the end, minus 1/2 mva squared. So things look quite different now, but there is something very profound going on, because if you look at the left hand side of the equation, you see that this sine theta and that sine theta cancels out as long as theta is not 0. Because if theta is 0, you got sine of 0. Sine of 0 is 0. We can't multiply and divide by 0. So theta equal to 0 is excluded, but that means we don't even have the problem, so it's okay to exclude it. So therefore, mgh, surprisingly enough, is what I have on the left side, which is no different than what I had in that problem, in the other, when I directly came down. So here if I write mgh as mgya minus mgyb, or it doesn't matter. So I can write now that mgya plus 1/2 mva square is mgyc plus 1/2 mvc square. But since h is the same, both cases are the same. So what the system is trying to tell you is when you are using these natural forces, gravity is a natural force, it's a universal force. This is a gravitational force related force, mg, as we discussed last time. Whether you go from A to B or whether you go from A to C, you get the same amount of work done. So the work done, therefore, is independent of the path. So whether I take this route or whether I actually take a route which is even more weird, like that, as long as we only have natural forces and not a dissipative force like friction, the work done only depends upon this height. How weird is that? How non-intuitive is that? It doesn't depend upon the path. So there is something going on which is fishy. So what's going on? Well, what's going on is that the potential energy is the problem, because the potential energy that we are calculating doesn't really care if you come down this way or that way in this case. And that is because the potential energy simply depends upon the vertical height. That's why I was setting y equal to 0, a 0 level of potential energy, and this is y equal to h in this problem. There's a 0 level of potential energy I defined on the ground level. But the detail of the path, that detail goes away as per physical laws itself. So it doesn't really matter what route I take. This is what's going to happen. Any questions? Okay. So I'm going to come back and push this thing a little bit further, because let's say the force is such that there is path independence. So the force is such that work done W is path independent. Okay. These forces have a name. Such a force is called a conservative force. Such a force is called a conservative force. Why am I defining this new thing called a conservative force? Because you need a conservative force for that to be valid, for energy conservation itself to be valid. If you don't have a conservative force, your energy conservation will not work. Friction is not a conservative force. Friction is a dissipative force. And therefore, for friction, you have to be very careful about how you use energy. I'm trying to warn you that if you're not very careful, you'll make a mistake. So to be very clear, I've dealt with a non-conservative force or a dissipative force over here. I can still calculate the work done, no problem. But I'm not using energy conservation law. I'm just calculating the work done. That I can do. Whereas over here, I am actually using the same work energy theorem idea to pull out energy conservation law, because I'm using gravitational force, which is a natural conservative force. So I've pulled two threads out of the statement on definition of work and on the work energy theorem. So the work energy theorem, so don't screw this up. The work energy theorem doesn't care about energy conservation. It's a more upper level, more high level statement. It doesn't care about energy conservation because I'm using work energy theorem for a dissipative frictional force. However, work energy theorem with conservative forces, or with a conservative force or forces, gives you energy conservation, which is what I've showed you. I pulled out two things out of the hat. So if I take a string and if I tie a little mass to the other end of the string, and if I take this around in a vertical circle, move it around, just because something is making a round trip, as long as there is conservative forces involved, there'll be no work done. So here, for example, I can go from point A to point B, and I have a work done. Okay? But then I come back from point B to point A, I have conservative forces involved. And although I have work done in going from A to B, it will turn out that work done in going from A to B and then work done in going from B to A is going to add up to 0 as long as there are conservative forces involved. So round trips will give me 0 displacement just by definition, as long as there are conservative forces involved. Very, very interesting, non-intuitive result. Just because I'm putting it up on the board, don't think that this is very easy and expected. It's not. Because it is only true for the special kinds of forces which we call natural forces, conservative forces, whatever, universal forces. It's not true for most of the other kinds of forces we encounter. Not true for dissipative forces that we have to deal with night and day. So, but since I'm on this problem, let me tell you something else. This is a string, as I said. You're taking the string and rotating this thing in a vertical circle. So, clearly, there will be a tension in the string. And that tension you can see if you're sitting here, the tension is this way. But your displacement as you're going around, this is the vector displacement, is that way. So what is the work done by the string? What is cosine of what? Which is 0. So this is weird, isn't it? So you are doing all this work by taking a mass at the end of the string and you are twirling it, so it's going around in a vertical circle. The string tension is always towards the middle. The displacement is tangent to the circle. So displacement over a given instant of time is like that. It's a super tiny arc here. That's your displacement. We already know that the displacement is going to be at 90 degrees to the tension T. So the work done is 0 in this case. Isn't that weird? In fact, I gave you a problem on that in the homework. So work done, if you multiply tension force with displacement, let's call it delta x because it's a very tiny displacement. Then you have to have a cosine of 90 between the two, and cosine of 90 kills it because it gives you a 0. You may be sweating doing it, but there is no work done. Now I'll change gears. I'll take any questions. Okay. I'll change gears. So far I've dealt with very simple forces. Simplest force actually I've done. Simplest force. For the most part, the simplest force meant constant force. The force doesn't depend upon displacement or distance. The force itself is constant. So if I drop this thing, mg is fixed. It doesn't matter where I am. Mg has nothing to do with the location. So, if you will allow me, if I say x is displacement and I have x to the power 0, what does power 0 mean? Something to the power 0 gives you what? So, x to the power 0 is kind of a way to say that this is going to give me 1. So, I can say that force here goes as x to the power 0 because force is mg. That's what I was doing for this case. What if I make it force goes as x to the power 1, which is the next simplest thing I can do? Well, I could do other things. I can make it force goes as x to the power of half or 1/3 or some other number. But I'll keep life simple. I'll just use integers. So if I just use integers, the next simplest thing I can make is force goes as x to the power 1. Now this is not a simple mathematical exercise. Suppose I take a spring. We have dealt with springs before. This is a massless spring, just like we had massless strings. So what a massless spring means is that this is a perfect transmitter of force because it doesn't use up any force in the spring itself. That's what zero mass means. And physically what it means is that the mass of the spring is very small compared to whatever mass is attached, let's say, to the end of the spring. Another way of saying that is you imagine that the spring mass is that you have a massless spring with an actual mass at the other end. That's what you're thinking you're doing. Now it turns out that long time ago, I think it was probably 1700s, don't quote me on that, I have to look it up. There was a fellow called Robert Hooke. And Robert Hooke observed that if you pull a spring, the spring actually tries to come back to its original configuration. A spring doesn't like being pulled, or for that matter, if you squeeze the spring would try to exert a force on the other side such that it can go back to where it used to be. So if I apply a force this way, the spring will give me, so this is force applied by me, let's say FSS. Those are my initials. And spring also has an S, but I'll call it Fs, which is that way. And let's call it Fs. That's the spring force. So I have to overcome this Fs to be able to push it out. And the amount of force I must give for it to be able to be moved out here should be equal to Fs. So suppose I say I take it from this point x0 to some point here, which I call, let's say, xa. So if I do that, if I pull it out and let it go, of course I remove my force, which means that this guy will take over, and this guy will ask it to come back here. But now let me ask you a question. So I released it, I pulled it like this. Imagine making this movie in your head. I pulled it like this, I was holding it steady, and then I released it. What do you think will happen in the middle? Will the spring come and obediently sit in the middle? Who thinks that that's possible? Nobody thinks that? So I let the spring go. Spring comes back. This is its equilibrium position. This is where it used to be. But you are telling me that it's not going to just stop there. Why not? What? It is picking up some speed as it's coming back, right? That's what our intuition tells us. If I release the spring is going to start speeding up. And as it speeds up, this may be its original relaxed position, but it's going to overshoot it because it's traveling too fast. So you see, this thing has very interesting dynamics, and we need to get into that a little bit. So what I'm going to tell you is that, first of all, we have to learn to calculate the work done by these springs. So I will just talk about the force I apply, FSS, and this is the displacement of this mass m at the end of the spring. I'll talk about that. So I've already told you that what Robert Hooke pointed out is that as x increases, this force increases. It turns out this force increases by this law, and this, by the way, is Hooke's law. Okay? So Hooke pointed out that as you stretch it, the force goes up linearly. So in other words, I have to apply more and more force to be able to pull the spring as I get farther and farther out. So in other words, there's a certain slope here, and we'll call it a kx. So therefore, the F in question is going to be FSS in this case. The force I apply is going to be k times x. The force the spring applies will be different. The force the spring applies will be equal and opposite, so that will be minus kx. The spring wants to bring it back. I don't want to bring it back. I want to pull it out. Yeah. Yeah. Yeah, we'll come to that actually. So Right now we are dealing with what would be an elastic regime. So elastic regime is a regime where this law works. Now if you pull it too much, then the metal itself begins to get deformed, or the plastic begins to get deformed. And then you enter what is called a plastic regime. That has nothing to do with real plastics as we know them, but from a physics mechanics standpoint, it's called a plastic regime. In the plastic regime, you don't have Hooke's law holding up anymore. In fact, this thing breaks down. So everything has its limit. So therefore, this shouldn't be too much. Bridges, for example, bridges are designed in such a way that whatever is used, they're used so that they operate in the elastic regime. So you have oscillations that bridges have, and they're supposed to have it, but they should be the elastic regime. The oscillations should be within so and so range and so forth. So the reason why bridges have to be replaced after a while is because repeated wear and tear eventually reduces this elastic regime, and it becomes very plastic, at which point the bridges can fracture, which is why bridges have a lifetime. Same with airplanes and cars and so on. They all have a lifetime depending upon the amount of oscillatory motions they have been subjected to. So there is something interesting I want you to learn now. I want you to figure out what is the work done as I pull this mass out. So we know that delta W is F times delta X. In this case, since F depends upon X, I should be a little bit more careful and write F of X times delta X. I am assuming that F of X and delta X are parallel. So therefore, the angle between them is 0, which allows me to ignore the cosine piece here. So, but because I have an F of X delta X, I have to be a little bit careful in the work done. If I calculate X here, I can say that by, so this is F of X. I can say that I stretch the spring from some point here, I think I call it XA, X initial I called, to X final. Okay, I took it from X initial to X final. So clearly, the force was varying. The force here was K times X. If K is the spring constant, the force here is K times X initial, and the force here is K times X final. The force is not fixed. So I have to be careful in calculating this quantity on the right-hand side out here. For the first time, I'm getting into trouble because I can't simply multiply the force times delta X in a blind way, because this force varies with X, and that's a bit of a problem for me. So what I'm going to do is I'm going to realize that multiplying Fx and X is actually the same as calculating this area. So I have to calculate this area, and I don't like to calculate areas like this because I have a slope on the top part of this. So what I'm going to do is something I've taught you very early on in this class, actually in the first lecture I think. I would just take the average force. So I will replace this area and trade it with that area and make it into a nice rectangle. So what will now happen is this piece here is going to be K X initial plus X final divided by 2. I have only 2 data points, so that will be my average force. Let's call it F bar right now. And the displacement that has happened, delta X, is going to be X final minus X initial. So now just to calculate delta W, I should be able to write K times X initial plus X final divided by 2 times x final minus x initial. Now that's very good because that allows me to actually construct a very simple relationship. But unless you know what I did, when I ask you to do this problem in the quiz or in an exam, I can guarantee you that 75% of you will make a mistake, and it's the very same mistake. So what will happen now is work done by me, delta W SS, is going to be k times, well actually k over 2 times, x final minus x initial times x final plus x initial, which means a plus b times a minus b, which means it's k over 2 times x final square minus x initial square. So this would be the work done by me on the spring. So this work done by me has deformed the spring. And having deformed the spring has gained energy. Because remember I said potential energy is the energy because of configurational change or positional change. In this case I have deformed the spring. I have changed its configuration. And in changing its configuration, what I have done is the work I did, that amount of work, ended up as energy of the spring. It's a conservative force also. So this is the work done by a spring. So now you see, you suddenly have a very powerful tool. That mass there, that mass can go. Once you let it go, let's say, what did I say there? X0 I called it. This is x0, this is xb, and this is xa. So it will turn out that suppose I take it here and release it. So this is how far I've stretched the spring and let it go. So the mass was here at t equal to 0. And I was holding it fixed. So it had no velocity. So no kinetic energy. All the energy it had over here was W equals 1/2 k xp minus xp square minus xa square. If xa is 0, just k xp square, right? So now I let it go. I let it go. And as we discussed a little while ago, as I let it go, the spring will really hurry to restore it back to its original position. And as it does so, it's going to overshoot. So at this point, what will happen is that because x0 is 0, this is x0, sorry. Because this thing we have set to 0 for now, let's say, original length is, let's say, 0, then what will happen is that at, so this is W at B, at point B. Then W at point 0 is going to be simply 1/2 m V0 square plus 0, because this piece comes from the fact that 1/2 k x0 square, which is what would happen here, is equal to 0. So therefore, all the potential energy that you had now becomes kinetic energy. So you can actually calculate the value of this V0. If you had numbers, you'll get a numerical value. So I can now write that at O, this point, I will have 1/2 m, because energy is conserved, 1/2 m V0 square, because this term's dead, and over there equal to 1/2 k xb square, because x0 is 0. I've set it to 0. So that means that I have a way now, I can cancel the halves, I have a way to find this V0, because this V0 is going to be k divided by m. Usually spring constant k can be a large number, and mass can be whatever it is. So V0 is k over m square root times x of b. And of course square root means plus minus. So just to write it a little bit nicely, I should be able to then write that V0 is equal to plus minus k over m square root times xp. In this case xp. So V0 will depend upon how large my xp is. If xp is very tiny, V0 will be tiny. That means I've stretched it by a little bit and let it go. If I stretch it a long ways and let it go, then I have a much larger V0. Now the reason why V0 is plus or minus is because once I let it go, this is what's going to happen. I stretched it here. This is my point, point B, right? I stretch it here at point B, and I let it go. So it's going to go like this. It's going to overshoot this point. The V0 is this thing going left, and then it's going to compress the spring. The spring is really squeezed here when it reaches this point, and then it's going to turn back around, and you see it's again going to overshoot and keep going forever. So this is plus V0 because it's going to the right, and that would be minus V0 because it's going to the left. So in other words, you actually have described the dynamics of a spring. These are the oscillations of a spring, and we'll come back to oscillations of the spring in great detail after a while, because that's a full chapter which turns out to be a relatively important chapter. The other thing, again coming back now to energy non-conservation. So far I used energy conservation to deal with the spring. But energy non-conservation, if I let a block slide, and if this is, let's say, the ground level of my calculation, so this is y equal to 0, this is y equal to h, and this starts from rest, then I have mgh as my total energy E at this point. So now I can trivially calculate what is going to be the velocity here, because energy is conserved. Let's say this point is x1. So I can write, whatever you call this point. Let's call this point A, and let's give it a certain velocity v1 because it's sliding down, it's speeding up. So I should be able to simply write 1/2 m v1 squared is mgh. M's cancel out. So v1 therefore is 2gh square root plus minus. In this case plus because it's going one way. But now there is something interesting. Suppose this area has friction, and eventually this mass comes and stops. I've already shown you when I started this lecture today how to calculate the energy lost due to friction, because friction force will be that way, you'll be going this way, so there will be a minus sign, and this energy that you have at point A will be completely lost by the time it gets to some distance B where there is no energy left. So that's an important basic application. I think I'm going to give you problems on that in the coming set and a few others. Yeah?
So the VO in the plus or minus radical over M.
Yeah.
That's the velocity at x0.
At middle.
Okay, so it's the initial velocity of the other. It's not like the initial velocity like when we had it.
No, because the initial condition was that I stretched it. That was so that was my initial condition. Now, it also allows me to find the velocity at any other position, because as long as I know what the position is, I can calculate the potential energy in that position. And since I know the total energy, I can calculate the kinetic energy and hence the velocity. All right, let's go to the quiz.